and I'm giving you sharing permissions, and you'll be good to go.
Great. Let me just share my screen. Okay. Before we get started, I guess it'd be useful for me to.
I'm sorry, just a moment. I will try to connect your audio to. How do we connect the audio to the? Oh, okay. So let's. Oh. Okay. Oh, so I have to close this. Ollie, can you hear me now?
Yep. Can you hear me?
Oh, okay, perfect. Everything is very good. Let me turn up your voice. Yes, we're good to go. Thank you very much.
Great. Well, thanks, Akin, for the introduction. I don't think I deserve all the epithets you threw at me, but I appreciate them anyway. I sort of learned a lot of what I know today and became interested in a lot of these topics because of Akin's own work. So yeah, I'm really, really excited to be doing this. Before we get involved in the sort of nitty-gritty of this, I think it'd be useful for me to know just briefly, like what your guys's, well, sort of three things. First, what the sort of background that you've had already in this SICSS session on remote sensing is, so I know sort of how to calibrate the remote sensing side of stuff, and then also what like academic backgrounds are represented in the room, so I know what language to use and when.
Yeah. So basically, this is a very interdisciplinary group of computer scientists, engineers, social scientists like sociology, psychology, political science as well. I would say like roughly equal like engineering, data science, and equal measure. But it's also like split between R people and Python people. But you are like the last lecture that we are having. For the last 3 weeks, they had a refresher in R, refresher in Python, data analysis and manipulation with R, data analysis and manipulation with Python, data wrangling with Python, data wrangling with R, and then more intermediate stuff on natural language processing with R and Python, geospatial analysis with R largely, then network analysis with R. And I mean, your stuff will basically be combining a lot of the stuff together, but for those that can follow, I think should follow. Those of us who can't follow will always return back to your like markdown and then rewatch this video and follow later. So I would say, like, just do in the way that you would want an earlier you to want to like taught these things. So just whichever way you want to go is fine with us.
Great. And then in terms of timing, I suppose we've got about an hour and change.
So we have about like an hour and a half, but it's up to you. That's like the maximum. So
Yeah.
if you just want to do 50 minutes, that's also like perfect for us. So it's that's up to you as well.
Okay. Well, I also appreciate that this is the last lecture in the series, so I won't run on for too long. Yeah. So I think broadly what I want to cover today is obviously like the specifics of this ship tracking project, the questions that we had, how we approached them, how we acquired and processed the data and extracted insights from them, but also sort of like how to think quantitatively and how to, come up with research questions, find data sets that might be able to answer those research questions, and move between sort of a general curiosity to specific insights. Because I think a lot of the challenge, even for people with like significant technical background, is you may be able to write the sort of functions and algorithms that you need, but you need to sort of know what you're looking for. So I'm going to spend a bit of time talking about the process by which we arrived at the questions, and almost like a diary of this project. So broadly, and if there are any questions, please just like put them in the chat. And I can't really see the chat at the moment, so if you just like verbally interrupt me.
Yeah, I will do that.
Great. Okay, so perhaps a good place to start is by sending everyone this link, which I will put in the chat. So the project that I'll be taking you through today is basically a project on tracking ghost ships that are illegally exporting Ukrainian grain. So what certain media outlets have reported, and other sort of sources have been reporting, is that when Russia takes over a new area of Ukraine, something that's been sort of systematically observed is that the military will come to the grain silos of the farms that they just took over. They will empty the grain silos onto trucks, and then those trucks will move from sort of the areas that are occupied down through here into Crimea, and specifically to the port of Sevastopol. So grain is being loaded from occupied territories, driven down on trucks to this port. And if we switch to a satellite map, we can see this port. And it's then stored in silos that look like this. And we can sometimes see some of the trucks that do it lined up in the surrounding areas. But in any case, grain is taken from occupied Ukraine and brought to this facility. There are a couple like investigative journalism outlets that have documented this process in quite a lot of detail. And there's evidence from a variety of different sources that sort of point to this occurring. So this is called the Avlita grain terminal in Sevastopol. And the way it works is the grain that's stored in these silos is pumped onto big vessels that come and dock here. And then those vessels, after they're loaded up, go elsewhere. So there's actually no vessel present here on this satellite image. But if we go to Google Maps, we'll see what it looks like when there is a ship at that location. So if we zoom in here, we can see a big grain carrying vessel. This is called a bulk carrier. And the bulk carrier has these big bay doors, and they open up, and then a sort of hose comes out and dumps grain into these open bays. So there's evidence that this facility is being used for the export of stolen Ukrainian grain by Russia. The theft of grain or other sort of economic like resources of this kind during war is a war crime. Generally a pretty bad thing. Generally something we might want to keep tabs on and sort of document. Now, both for sort of accountability purposes, but also, as an academic endeavor, being able to develop methodologies that help us, understand this type of phenomenon, probably in the long run leads to a better ability of like public bodies to keep track of these sorts of things, and hopefully, that information will be sort of useful in the long run to, keep track of how much grain was stolen from Ukraine. There are a bunch of reasons one might want to do something like this. Now, if we want to quantify how much grain is being stolen, or how many vessels are coming and going from this place. Well, one of the primary sources of data on ships is called AIS data. AIS stands for Automatic Identification System, and all ships above a certain length, certainly all commercial vessels, have to carry a little box that is a GPS sort of transponder, and broadcasts their location and identity and other information about themselves using VHF radio, so to the world. And this is like an IMO, International Maritime Organization requirement. So it's a legal requirement. And it's primarily for the purposes of safety. So it's primarily so ships don't crash into each other. So if we zoom into Istanbul, we can see a bunch of ships transiting. And, maybe after this, or I don't know how close you guys are to the Bosphorus, but if you can sort of peer over the Bosphorus while looking at this website, marinetraffic.com, you can see which ships are passing when. So this, for example, we can see that there's a ship called the Zagreb, and it's heading through the Bosphorus right now, and its destination is Eden. So if we click on it, we'll also get some more information about this ship. So ships, especially cargo vessels, are constantly broadcasting their position and identity. So this is a fantastic resource for tracking the movements of ships over time. And many websites and platforms aggregate this information and store even historical data on this. So naturally, if we want to quantify the amount of grain being exported from this grain terminal in Ukraine, in the same way that we can now in real time sort of see how many ships are in the Bosphorus, we would maybe want to go over to the port of Sevastopol and see what ship activity over there looks like. Well, you'll notice that it's blank. There are no ships currently at the terminal that we were interested in. So that's fine. That's right now. Marine traffic has a historical playback feature. Let's look at ship activity in the past 7 days. Okay, so this is now a historical playback. So if I, for example, if I go elsewhere, if I go back to the Bosphorus, we'll see what the historical playback function looks like. We'll see ships moving around, right? So this is 3rd of July, 2023, moving onwards, right? We can see historical ship movements, and that's what this looks like. Okay, great. Let's look at a port in Ukraine, occupied, in non-occupied Ukraine. If we look at a port, we can see that there are ships present in the port, and they dock alongside these berths. So we see the outline of the ships, right? And this satellite map is static, right? It's not showing current satellite data, but we can see that there are ships present at some of the terminals here in Odessa. So if we go back to Sevastopol and we try to do this playback, let's see what happens. Okay, let's continue the playback. Remember, the area that we're interested in is this berth right here. So if we do this playback, we get still a whole lot of nothing. We can skip ahead, July 5th, July 6th, July 7th, July 8th, nothing, nothing, nothing. So you would think, based on the ship tracking data, based on open source automatic identification system data, AIS data, that no ships are coming back and forth from this terminal in Sevastopol. Let's try adjusting the date range to a different period. Let's adjust the date range to last summer in, let's say August. Well, what's happening? Let's say August 1st to the end of August. So, or the first week of August. Let's try that. Okay. So if we do a playback through August of 2022, we will still see no ships coming or going from this terminal. We've got something over here, but it's too small to be a grain carrying vessel. And we can keep skipping along. And okay, I think I've made the point that basically there are no like large vessels, of this size that are appearing at this grain terminal in Sevastopol. Now, this sort of limits our ability to track the export of stolen Ukrainian grain using this data source. But naturally, this is not the only source of data that we have access to. There are many other sources of data, and one particularly relevant type of data that we might think of using to supplement this ship tracking data is satellite imagery, right? In the same way that from this base map that we're looking at, we can clearly see ships in various places. Well, in order to confirm in order to confirm the presence or absence of ships at this terminal, we might want to use satellite imagery. Now, we could use optical satellite imagery. We could just load in a photograph like this, or we could use a different type of satellite imagery, which is called synthetic aperture radar imagery. Now, both work fine, right? There are simply different analytical choices that need to be made depending on which type of imagery we're using. Now, we're now entering the 500th day of the war in Ukraine, and we are presumably interested in tracking this phenomenon into the future, right? As long as it lasts. It may last, I don't want to speculate, but we want to be flexible in terms of being able to ingest more data in the future, right? So we want to develop a pipeline that is going to be relatively simple and at a minimum can automate the detection of a ship at this location, automate the detection of like the presence or absence of a ship at this berth, right? So one thing we could do is just load in a bunch of optical satellite images that look like this. The issue with that is we have then two sort of choices when it comes to ship identification using optical satellite imagery. Does anyone want to sort of guess what if you had to do that? Well, there's obviously the manual way, right? We could, given a stack of optical satellite images of this area, we could just sift through them manually and write ship, no ship, right? But given that we're in day 500 of this war and we want to be able to run this into the future, that might be cumbersome, right? So does anyone want to hazard a guess as to like how we might approach automating the identification of ships in this area using optical satellite imagery?
So I think they might have some ideas because they also receive 3 tutorials on computer vision with Python. So actually, you would, I mean, most of you are new to computer vision, object detection, and that kind of stuff, but they also work with synthetic images as well. So any guess on how, through a satellite imagery point of view, you would detect ships using, you're talking about computer vision, right? Or
Yeah, that's sort of where I'm leading people to.
yeah. So any ideas? Because you would know. Yes, like you're not experts on computer vision right now, but I mean, you got like 3 very good tutorials on it. Any ideas?
Object detection model trained on satellite images on ships from satellite images can detect.
Can you hear or
Yeah, I heard an object detection model trained on satellite images.
Mhm.
Yeah, yeah. So that's a great solution, right? What might be the difficulty in implementing that in this area, or just implementing that in general?
the cloud cover?
Cloud cover. What if, you know, this is a sort of clandestine activity? They're doing this illegally. What if they load at night?
Hmm.
We can't see them at night either. Just in terms, we're also assuming away a very large component of this task, which is the training itself, right? Object detection models notoriously very difficult to make them generalize well, right? So if you have, you know, you could download some training data, and indeed, in part of this tutorial on the remote sensing for open source investigations tutorial that I have put together, there is a module on object detection in optical satellite imagery, but you either need a massive training data set, in which case you also need significant compute resources, right? You need access to GPUs, which are, it's, you know, not that easy to do, especially for long training times. And you're going to want to train the data in a way that like fits the context, right? So if you get, even if you're very lucky and you find a pre-trained object detection network that's been trained on ships in the resolution of satellite imagery that you have access to, it might get confused. Perhaps, you know, it was trained on ships that are at sea. It might get confused by ships that are next to land, because a ship that's on a pier looks very different from a ship that's like adjoined to a dock, if that makes sense. So we might worry about cloud cover. We might worry about these this loading happening at night when optical satellite imagery is unavailable because it's dark. We might worry about either finding a pre-trained object detection network that generalizes well enough to this area. And if we're so lucky as to have that, we would then probably still have to fine tune it to work on this area. So it certainly would be possible, but it would be quite difficult. Now, the approach that we took in this project was slightly different, and it involved a sort of a combination of the two. But in order to simply identify whether or not a ship is present, we used a type of satellite imagery that is not optical. Rather, it uses radar. So briefly, there are two main types of satellite imagery. There's optical, and so these are called passive sensors. And what these sensors do is they passively collect reflected sunlight from the Earth. So the sun emits light in the visible, well, it emits light, and then these satellites capture the sunlight that's been reflected from the Earth and simply take a photograph in the same way that a camera works, right? This is subject to a lot of the issues that we just talked about, right? Clouds, nighttime, the complexity of the actual task of identifying like the shape of a ship. We'd have to use a neural network to do that, right? But this other class of satellites called synthetic aperture radar satellites function by sending a pulse of radio waves towards the Earth and then listening to the backscatter. So listening to the echo of that pulse of radio waves. And these are called active sensors because they emit their own, they create their own illumination, as it were. And the great thing about radio waves is that they can penetrate through clouds in the same way that I can get Wi-Fi in this room despite the router being on the other side of that wall. Radio waves can penetrate through sort of sparse surfaces, and because the sensor provides its own illumination, it can image at night as well, which means we can get imagery from a particular location, regardless of whether or not it's daytime or nighttime. And the third advantage is that because the way synthetic aperture radar works is, if we're sending a pulse of radio waves down to Earth, and that pulse hits a very flat surface, say the sea, then that provides a perfect sort of surface for those waves to reflect at an angle and go back off into space, right? So if we send the pulse down to a very flat surface, very little of that radio wave is going to get reflected back to the satellite itself and get picked up. So when we have a flat surface and we're concerned with detecting whether or not the surface is indeed flat or there's a 300-meter long hunk of steel on that surface, that's actually a much easier task quantitatively, like in terms of the nature of the image processing that we have to do to detect such an event, because we can sort of, I guess you could call it like very simple segmentation, where the result of a synthetic aperture radar image, like the raster that we're given from this type of satellite, is simply a matrix in which each pixel tells us the amount of the signal that came from the satellite that is reflected back to the sensor. So that may be a bit confusing. So if we open up Sentinel Hub, I'll show you what synthetic aperture radar looks like, so maybe you get a better idea of what we're talking about. So let's load some imagery. Sentinel-1. This is the satellite that we're using. Now, this is open source satellite imagery from the European Space Agency. And to show you what I'm talking about, I'm going to load this imagery and let's just do black and white because that's less confusing. So as you can see here, we've got a radar image of this port in Spain. And we can quite clearly see the difference between the on-land area, right, where we've got things that are reflecting the signal to the satellite. And then we've got the flat surface of the sea, which is reflecting much less to the satellite, right? Even in the darker regions of this urban environment, there is some sort of return signal, right? There's some stuff on the ground that is reflecting the signal back to the satellite, versus when we look at the open ocean, there's nothing to reflect it. Therefore, the signals bounce back off into space and are not captured by the satellite. Low return signals show up as black in this raster. High return signals show up as white. And if we go over to this area in the sea, we can see ships. And ships show up very cleanly in synthetic aperture radar imagery as these white blobs. And that's because we've got a region here that's totally flat, where nothing is reflecting the radio waves. And then we've got a thing in the middle of the flat surface that is then reflecting those radio waves. So what we can then do, especially if we're concerned with identifying ships at a particular location, is make one assumption, which is that an area of water in which there's nothing present will have a very low return signal. An area of water in which something is present, like a big ship, will have a much higher return signal. And in order to turn those precepts into, to translate that into an algorithm that identifies ships, we simply have to, instead of training a object detection neural network on thousands of labeled images of ships and then fine-tuning it to an area, we can say, if there is a return signal that is above a certain threshold at this point, consider that there's a ship present, and if not, consider that there's no ship present. That's all that we have to do to identify whether or not a ship is present at a certain location using synthetic aperture radar imagery. Any questions about that process before I go into it a bit more?
Any questions? Yes, Jawad.
So here, can we use LiDAR data here in this case, because the LiDAR data, they use the lasers from them. They might be precise in this case as well, right? So I mean, I'm just having that question. I mean, like along SAR data, I mean, can we use LiDAR data as well in this case?
So how does LiDAR compare to this specific like image that you're getting? Like, can we use LiDAR?
So LiDAR, like in principle, very similar, right? There are LiDAR satellites, but for sort of technical reasons, basically, the LiDAR satellites that are currently open access, I think there's like JEDI, it's called, and these satellites they use like a laser, basically, and a laser is much more focused than a sort of a pulse of radio waves. So these LiDAR satellites, so the short answer to your question is, in principle, this would work the same with LiDAR, yes. In practice, the nature of LiDAR imagery is that you get these really long, really narrow strips, and they don't cover a large enough area usually to provide sort of sufficiently regular coverage of an area of interest. So the swath refers to sort of the width of a satellite image, and the swath of a LiDAR satellite like JEDI is very, very narrow. I don't know exactly how narrow, but quite narrow because it uses a laser, versus the swath of a synthetic aperture radar satellite, which is about 5 kilometers in width. So if we, I think they mosaic these images together on Sentinel Hub, but generally we'll look at a single SAR image, but we get quite nice large aerial coverage with synthetic aperture radar, and we get quite regular revisit times for the same place on Earth. So for this particular area, we get satellite imagery, we get radar imagery of this port. I mean, you can see it here multiple times per week. So let's zoom into our port. Sorry, does that answer your question, or should I? Or are there any other questions about?
Yeah, so like LiDAR is just narrower, these are like wide. So ideally perhaps it would be like you get wider area images with this and then find a point of interest. If you have a drone nearby, just go LiDAR it and then have higher precision stuff, but it's more expensive as well. So yep.
Also, good luck flying a drone over Crimea.
Yeah. Yes.
I wonder how sure we are that there is no way to escape from the radar. And for example, if you said radar detects after a certain threshold, I wonder this threshold because for this, maybe they will need big ships, but for example, for other kind of illegal activities like human trafficking, they may need just like smaller ships. So can we also detect smaller ones, or how small?
That's a great question. So I heard the bit about detecting smaller ships. Was there? But I didn't quite hear the first part of the question.
Yeah, so for example, if we were to do like a similar investigation on like human smuggling networks in the Aegean Sea, for example, like, can we reliably do this? Or like, what's the level of precision that we're working with there?
Yeah, great question. So the spatial resolution of Sentinel-1, so Sentinel-1 is the name of the radar satellite that we're using here, and it's a European Space Agency satellite, and it all of the data is open access. The spatial resolution of Sentinel-1 is 10 meters per pixel. Now, obviously, the minimum size of an object that you would want to detect using radar imagery would kind of have to be larger than one pixel of that image, right? So it'd have to be at least 10 meters in length. But even with objects that are 10 meters in length, or even 20, 30 meters in length, you know, just intuitively, you might find it reasonable to conclude that like detecting something that's 300 meters long and 50 meters wide is easier than detecting something like a dinghy that's 10 meters long, 20 meters long, and like a meter wide, right? So you might get lots of false positives. It probably wouldn't work as well. So this application is geared towards identifying very large cargo vessels, and it works quite well for that. And it would be a different ballgame if we were intending to identify much smaller vessels. So yeah, any other questions before I move?
No, we're good, thank you. Yep, we can continue. Oh, sorry. No, it's, I think, yeah, there's a Ollie as well. Oh, Ollie, are you there?
Yeah, I think I'm back.
Okay,
You hear me?
yes, okay,
Is
we can hear you now.
deep irony of the Wi-Fi in the Center for Advanced Spatial Analysis cutting out all the time, but
Okay.
such is life.
No, it was
okay,
fine. It was
so
fine. Yep.
cool. So I'll move into the I'll do like a code walkthrough.
Yeah.
And maybe some of these concepts will become more clear when we have a look at the code. So I can send you the link for this, but
yeah,
it will require a Google Earth Engine account, which if you have one already, great. Unfortunately, there's like an approval process for Earth Engine. I think they auto approve everyone, but it does take a day or two to happen. So for now, I'll just do a walkthrough, and then if you want to attempt it later on in your own time, you can do so. I'll just send the link in the chat.
Okay.
Okay. So for now, it's mostly that I just want you to sort of see the code to see actually how simple this is, and to get a sense of like the way we would approach such a task. So first, I have to load all of my packages. Or actually, before I walk through the code, let me show you sort of the application that's built on top of it, so you can get a sense of how we use radar imagery to establish the presence or absence of a ship in a given area. So, and this one we can all follow along on, and I will send this link to the chat as well. It keeps hiding the chat from me. Very rude. Where did they go? Sorry, one sec. Can I send it to everyone? Okay, there. So if you click that link, it will open this application that I put together called the ship detection tool. And I'll show you how it works, and then we'll peek under the hood at the code that enables it to run. So if you'll recall, when we went on marine traffic and we did a time lapse from August 2022, there were no ships that were present based on their AIS signal, right? There were no transponder signals that were active in that area. So using the principles that we just talked about, right? Like detect the ship if the satellite detects the presence of an object on this flat surface in sort of a binary way, right? 0 is flat surface, 1 is there's a ship. If we do that, then we can infer whether or not a ship is present at this location at the time of a given satellite image. So what this tool does is it loads in a year's worth of radar imagery, and then it runs a ship detection algorithm, which is very simple, and we're going to walk through it in a second. And then it outputs a graph, a plot that shows you whether or not a ship was detected within the bounds of this user-specified rectangle that we can change at a particular date. So remember, AIS said no ships present in all of August 2022. So if we start February 22 and we go all the way to June, July, and we zoom in, we get to the end of July, and we see that it's detecting a ship present on August 5th, August 13th, August 18th, and all the way through to September. So if we click on any point here, it will load a radar image of that from that particular day, and then the detection, which is shown in green. So we can see quite clearly that this white blob, right, the surrounding area is black, meaning that there's nothing reflecting the radar, the radio waves. But the area right along the berth of this grain silo is white, meaning there's some large object present there that's reflecting the signal. And if you look closely, you know, we have a base map image from Google Maps, and the size of this radar signature that's being reflected to the satellite is basically exactly the length and position of a ship that is present in an optical satellite image from a different time, right? So we can be reasonably confident that this is an accurate ship detection at that location. And we can click on different dates, right? We can click on August 5th and see, yeah, probably another ship present. An interesting detail here, this is most likely a tugboat. Tugboats are necessary to move ships in and out of, well, to berth and unberth ships from these piers, because they can't do it using their engine. So this is probably a tugboat that's coming along to help this ship. So we can see that on August 5th, there was a ship present at this location. August 13th as well. Let's let that load. Another big ship is present. But okay, what about the dates where it's not picking up anything? Then we can see there are some blobs here, but they're not the size or shape of a ship. Now, I will spare you the guessing, but you can sort of tell that these blobs align with the position of the cranes that are mounted on the side of the dock, right? So this signature here is probably, and this one as well, there is something present in this area, but it's not one large continuous 300-meter long chunk of steel, right? So what we're going to want to do is not only check whether or not there's anything present in this box, but set some limits on the sort of shapes that we want in this box, right? We might want an object of a particular length or a particular area, like a minimum sort of length to consider it a true detection of a ship and not, you know, a tugboat or a crane hanging over the edge. But in any case, we can use the finished tool to see that even though there was no AIS data showing ships being present in this location, if we load up a radar satellite image, we can see that on many days, actually, in the summer of 2022, and indeed all the way through to the present day, there are ships that are present at this location. And what this workflow also does is tells you how many detections are recorded in a particular year. So in this case, we've got 62 detections in 2022. Now, remember, we don't get a satellite image every day, right? So the maximum number here is not 365. The maximum number here is the total number of satellite images that we have of this area over a certain year. And that'll be about, I think, like 180 or 190. So quite a few ships present in this area. And we can fast forward now to 2023 as well to see how the situation has changed. So we can see that actually in 2023, there are more days in which a ship is present at this pier than days in which a ship is not present at this pier. So if I click here, for example, you see we've got a ship there, and here as well. So there are 47 detections so far in 2023. And this is all well and good, but maybe we want an added layer of certainty. The original remit of this project was to use only open access data, but through Bellingcat, who have a relationship with the satellite imaging company Planet, we were also able to get high resolution optical satellite imagery of this area as well. And so what we ended up doing was creating an image mosaic with all of the days in which a ship was present using optical imagery. And then on days in which there was no optical imagery, we loaded in an image from the Synthetic Aperture Radar satellite. But what we can also see is in consecutive days, right? Here, we've got July 2022. We can see probably the same ship present in consecutive days, one with an optical image on the left and one with the corresponding radar image on the right. And in total, we found over 180 such detections. So sometimes, you know, you can see multiple ships present at that berth. It's important to note that over this entire period, there were virtually no ships that were detected via automatic identification system. So what the ships are doing is turning off their transponders, showing up to this port and loading grain, and then exiting the port and turning it back on. So we can combine this with other sources of satellite imagery, optical imagery, even though this stuff, the high resolution stuff, is typically not publicly available. And if so, like very expensive, unless you get lucky, as we did. So we relied primarily on radar imagery. So let's go to the, let's see how we would actually conduct this detection, because it may seem complicated, but actually it's quite simple. What I'm doing right now is authorizing Google Colab to use my Earth Engine account. Google Earth Engine is a cloud computing service that stores petabytes of satellite imagery and allows users to run spatial computations on Google servers. That's very helpful because spatial data sets, satellite imagery in particular, tend to be very large, and the computations, therefore, very expensive. So this is a way of running things very quickly. It's free for now. You never know with Google, but it has been for the past 5 years, and fingers crossed it stays free for research purposes forever. But you can sign up for an account if you just Google Earth Engine. But in any case, I have now authorized Earth Engine, so I can use it via its Python API. So first, what I'm going to do is define a geometry, so define an area of interest. Now, I'm actually not going to be looking at the port in Sevastopol. I'm going to be looking at an anchorage nearby, which is an area in which ships sort of hang out while they wait to go into a port. So that anchorage is defined by these coordinates, and I turn it into a geometry object just by passing the coordinates in that format. And now we have a variable called AOI, which stores the geometry of the area of interest. Next, I'm going to load the satellite imagery, and I'm going to load Sentinel-1 ground ridge detected imagery, it's called, and I'm going to store that as a variable called S1. So this S1 variable, you can imagine it as containing basically a stack of raster files, of image files that are like synthetic aperture radar imagery. And each one of these satellite images has metadata as well. And part of that metadata is obviously the time of acquisition. So the first thing we're going to do is to sort of cut this down to size and only use the amount of data that we need, is to first filter the Sentinel-1 image collection using the area of interest. So I'm going to discard all of the radar imagery that's in areas of the world that I don't care about. And then I'm going to filter it temporally. And I'm going to just load in imagery from 2022, from July of 2022. And I'm going to select the VH polarization. I don't have time in what remains to explain polarizations, but don't worry about it. For our purposes, it's not particularly important. In general, what we're dealing with is simply the strength of the signal that's reflected to the satellite. So then I've got a list of images that were taken between these dates in this area. And that's what this variable image list is called. Any questions so far?
No, we can continue. Yep.
Cool. Okay, so this is it right here. This cell in the notebook, this is the ship detection algorithm. It's nothing fancy. It's very, very straightforward. So we've got two functions. The first function is called run detection. That's going to surprise run detection. And then the second function is called ship length. And what that's going to do is it's going to measure the length of the detected object on the surface of the water. And we're going to use the length of the object to discard objects that are too short and maybe don't correspond to ships, certainly not cargo ships. So let's just go through it line by line and run it so that we have these functions. The first line, so it takes two arguments, right? The first argument is image, it's an image, and then the second argument is a length filter. So this is going to be the length in meters that we want to use as a threshold for ship detections. So in this case, I'm using 100 meters. I want only detections that are longer than 100 meters. This will weed out a lot of noise. So the first thing I want to do is from the image, get the metadata information that corresponds to the time, the date and time that the image was taken. And I'm going to store that as a variable called time. It's stored as a timestamp, so I'm using datetime to convert it from a timestamp. and so it's nice and formatted like a real date. So now we know the time at which the image was taken, and the date. So that'll be useful if we want to plot detections over time, for example, right? Which is what we did previously. This line right here is responsible for like 80% of the work of automatically identifying ships from synthetic aperture radar imagery. This line right here. All it's doing is it's taking the image in which each pixel has a continuous value that corresponds to the strength of the return signal at that location, and it is setting a threshold of -15. So typically, the satellite receives less return signal than it's sent out, right? That makes sense. It'd be very strange for the satellite to pick up an even greater return signal than the magnitude of the signal than it's sent out, right? There are cases in which that happens that are very, very interesting, and allow you to identify like military missile defense systems from radar imagery, but we're not going to talk about that. In general, the return signal is lower than the emitted signal. And through trial and error, and we'll experiment with this in a second, we can set a threshold almost sort of heuristically at -15. So in general, the range of return signals goes from like around -30 all the way to like shallow negative, so like -5 or around 0 for something that's really strongly reflecting the signal. So we pick a point sort of roughly in the middle there at around 15, but we'll play with it in a second to see how it changes things. In fact, we can write a variable called threshold. Okay. And we'll play with that to see how it changes things. But then we're going to threshold the image, and we're going to say anything that generates a return signal above -15 is going to be considered, an object, a ship, and anything below that is going to be considered water. So then we're left with a raster, right? Basically a matrix of ones and zeros, in which each pixel now has a value of 0 or 1 based on whether or not it's above or below this return signal threshold. After that, if we want to move from this matrix to a list of objects, then we have to reduce it from a raster to a vector. And we're going to do this is broadly in the realm of blob detection, as it's known. The scientific field is actually called blob detection. And all blob detection does is finds ways of grouping together values in a matrix that are similar and that are adjacent. So what we're going to do is, if you visualize the raster as a square, a matrix of zeros and ones, we'll have a background of zeros, right, of open water, and then a region with lots of ones that are next to each other. And all this line of code does is looks for regions with adjacent values of 1. And then it will find the contours of a region where there are several ones side by side, and it will group all of the ones that touch each other into one sort of shape. If we go back to this tool, the black and white image in the background is the raster, right? It's this matrix of zeros and ones. And I've sort of smoothed it a bit so we get a little bit of gray, but you should imagine it as being like relatively binary, zeros and ones. And then this green area represents the result of blob detection from that. So it's grouping together regions of pixels that have a value of 1 that touch each other. So that's the result of this line here. And then once we've got that, we want to filter each one of those blobs by its length. And quite simply, we do that by calling the, I don't know why this is, oh yeah. Well, first we want to discard the region that is, it also identifies one macro region for water. And we want to discard that area. So that's what this line of code does. It says keep only the blobs that have a label of 1. Keep only adjacent regions where the pixel values are adjacent 1s, not adjacent 0s. So get rid of all of the water. And then what we want to do is iterate through the list of detected blobs that we have, and we want to calculate their length. So the way we do that is using this ship length function. So ship length takes a feature, a blob, and it will take the, it will first create a box that fits the sort of maximum and minimum. It will basically find the smallest box that fits that blob. And once we've got that, it's simply a matter of taking the top left coordinate of that box and the bottom right coordinate of that box, and then measuring the distance between the two of them. Now, obviously, this is an imperfect way of measuring length. It's somewhat sensitive to orientation, but as a sort of rule of thumb, to filter detected objects based on their rough length, give or take a couple meters, this technique is very fast and very efficient at getting the length of each detected blob, which is important given that we want to apply this to dozens, if not hundreds, of satellite images in one go. So this is also the advantage of using relatively simple methods, which is that we can apply it. This, we took it for granted, but this ran on a year's worth of satellite imagery, hundreds of images in a couple seconds. And that's partially thanks to this being a cloud computing service and running on Google servers, but it's also because we're using very, very simple methods for detection, right? We are using thresholding and vectorization, nothing more. No neural networks, no big bulky models, just thresholding. So once we've mapped this, once we've gotten the length of the feature, and we're also calculating the area of the feature, we set those as attributes for each one of the detected blobs, and then we can filter the blobs by their length. And we only want to keep blobs that are greater than the length filter that we've defined. And then finally, before we return this data set of detected ships, of blobs, we want to print out the date of the satellite image and the number of ships in the area. And that's simply just the length of this feature collection. Okay, so that's it. That's all there is to it in terms of detecting ships using synthetic aperture radar imagery. I'm going to run all of that now, and then I'm going to ask you if you have any questions, because maybe it'll help to see it, to sort of visualize what's going on. So we've altered this run detection function to have a threshold value. Let's keep it at -15 for now, but then we'll change it to see how it changes. So right now, what we're doing is we're loading an image from the image list. We're running detection on it. We're calling our run detection function. We are generating a map. We're centering this interactive map down here around our area of interest and setting the zoom level. Then we're adding 3 layers to our map. The first is the sort of raw synthetic aperture radar image. And we're coloring it as minimum value 25 and maximum value -15, which is our threshold. Then we're adding the detected ships, the blobs, and we're going to color those red. And then we're adding the area of interest as a blue rectangle. And then we're going to see that down here. And that's the result. We can toggle the visibility of certain layers, or we can just rerun this again without the AOI. And we can see that in this satellite image, which was taken on the 14th of June of July last year, in this area, this anchorage, which happens to be near Sevastopol, this is the extent of that satellite image, we've got a bunch of ships that are present, and we've detected from the underlying image, we've got these red detections which correspond to the detected ships. Now, we've got a lot of small ones here that are missing from our detection because we've set a length filter, right? We've set the filter to 100 meters in length, and we've detected 33 ships as a result. So what if we mess with the length filter and make it shorter? Let's say we make it 50. Then we're going to get a lot more of these ships. But you know, when I was explaining this, I obviously simplified things slightly. The surface of the water is not perfectly flat at all times, right? There are waves. Sometimes there's more wind, so it's rougher. So there is some noise. But in any case, a ship is generally sort of clearly visible in the water as this region, this bright white region. So all we're doing is basically binarizing the raster into low return signal and high return signal areas over water. And then we're grouping together adjacent areas of high return signal and grouping those as a singular ship. And then filtering out, we're then computing the length of the detections and filtering out ships that are below a certain threshold. So that's all there is to it. Any questions about the way we're conducting ship detection here?
Any questions? Like the usage of satellites, the setting of the parameters to detect, the methodology of detecting, assessing whether we have, you know, detected correctly. I remember like some people were thinking about, it was you guys, right? Like trying to detect gentrification through like satellite imagery as well. So it would be, I mean, I suggested in that research project to use like night lights to measure gentrification over the years, expecting like higher amount of night light in a gentrified region compared to like a previously gentrified region. But this is like an excellent, I think, way of thinking about spatial data and spatial detection that I think many people here will first have to, you know, go to Google Engine, get the API, redo this, and then maybe like ask questions to you via email. Right now, like this looks extremely interesting, but I think more questions will pop up as people, you know, try to replicate this and try to do their like own analysis. At which point you're going to get a ton of emails, I'm assuming. But yeah, no, I don't think any questions again. Don't be shy. There's no such thing as a bad question in Summit Institute. So okay, I think we can continue. Are you going to continue or are you finished?
Yeah, so I don't know, maybe to sort of conclude on, you know, we zoomed in quite a bit now and we've gotten into the weeds of this. You know, we've got something that plausibly seems to identify ships. Now, obviously, we want to validate whether or not, in order to choose a particular threshold, as you say, like, these parameters, in particular, the threshold parameter for what the minimum cutoff for the return signal, how do we choose that? If we go up here and we set the return signal threshold to -25, then we'll see that this performs very differently, and we get probably lots of false positives, and we might even get an error because it's making one giant blob. But okay, yeah, so we've got 3,410 detected ships if we set the threshold too low, right? And it's detecting basically every wave, every little irregularity on the surface of the water as being a ship. So, okay, how do we set a threshold? This -15 maybe seems kind of arbitrary. Well, if we approach this in a sort of rigorous way, what we do is we go to an area in which we know we have good data. So to A, validate the model, and B, calibrate it, i.e. to pick a threshold that makes sense. What I did was I looked at a legitimate port, a port in which all of the transponders, the GPS data that we were looking at here, is on and accurate. And this was in the port of Odessa. And they have 5 grain terminals in the port of Odessa. So we're using similar ships. And I drew these sort of polygons. This one actually should be oriented flush against the berth here, but that's fine. And I set up a like a standard sort of confusion matrix setup where I measured whether or not a ship was present using AIS data, so whether or not there was a GPS signal of a ship in this area on a particular day. And then whether or not, and obviously that's binary, right? There's either a ship or no ship. And then the predictions of the model from the thresholding and again, these are binary, ship or no ship. And we just did a confusion matrix. So based on like purely thresholding and no, fancy neural networks, no object detection, nothing like that. We have accuracy of over 90%. And it's also worth noting that this is like pretty bad validation data in terms of it's probably understating the accuracy here, because it's possible that a ship was present, in the morning and then left in the evening at the time in which the satellite image was taken. So the maximum sort of agreement between the AIS data and the actual sort of ship detections is probably never going to be 100%. But in any case, we've got a situation in which we can validate this model in a region in which we have good, like reliable AIS data that's not being manipulated. And then we can run the same workflow in an area. And if we plot these over time at a specific berth, we can see like the number of ships detected by AIS, by their GPS signal, and the number of ships that are detected via satellite are in close agreement almost all the time. And then if we go to an area like Sevastopol and we run the same workflow, porting in AIS data and comparing it to the satellite imagery detections, we get a situation in which immediately following the onset of the war, which is shown by this dotted line here, before the war, we had a situation in which the synthetic aperture radar satellite was detecting a couple of ships over time, but there were sometimes corresponding AIS signals. There were consistently more satellite images, satellite detections of ships than reported AIS detections of ships. So there's definitely shady stuff going on prior to the onset of the war. And it's worth bearing in mind that this area, Sevastopol, has been under occupation since 2014 and has been under international sanction since 2014. So there's still motive to turn your transponder off when visiting it. But what is interesting about this is that at the onset of the war, we get a total flatline of AIS signals and an increase, like quite a substantial increase, in the satellite detections over time. So what we're able to see here is that this port is actually busier than ever, but the nature of that traffic is virtually entirely composed of ships that have turned off their transponders. And because we now have the lengths of the ships as well, we can measure the length of the blobs, and there's obviously a relationship between the length of a ship and its carrying capacity. We can use that to estimate using like linear regression, not only how many ships were present, but knowing how long they are, how much grain they were likely transporting. So this is, one part of a larger project, but, to zoom back out, what we set out to do was, starting from a couple of meticulously verified accounts of grain being loaded from occupied regions of Ukraine, transported via truck to a port, loaded onto a ship, and then exported by that ship, from a couple instances of investigative journalism that identified such behavior. We've now set up a workflow that is capable of keeping track of ship traffic at this specific port, and indeed anywhere on Earth, really, that is independent of AIS, of sort of ship reported location, which is not only manipulable, but almost always manipulated in situations in which, we might want to be paying attention, such as grain smuggling. So we did that not using like super complicated methods, really large models. We did that simply using open access radar imagery from the European Space Agency and thresholding. And we're able to achieve quite good results with just that. So I hope this has been sort of an informative process, not only in, obviously you will have tackled more computationally complicated projects throughout this series of workshops that you've just attended, but I hope this has been sort of illuminating in terms of how you might start with a particular question, think about the utility and limitations of the different data sets that are at your disposal, and how you can combine two sort of imperfect data sets to yield insights on a particular question that you might have. In this case, the volume of unreported ship traffic at a sanctioned grain terminal in occupied Sevastopol. So that's it from me for today, unless anyone has any questions now. But otherwise, play around with the links that I sent you. And if you have any questions in the coming days, feel free to shoot me an email and I'll try to get back to you.
Great. So basically, the reason why we had Ollie like as a last lecture is that like throughout this summer institute, I talked to each and every one of you about the necessity for the computational social science discipline to grow like out of its huge reliance on Twitter text data, because like in previous years, almost like nearly the entirety of the projects were Twitter text, which is fine. I mean, Twitter text is good, but the whole, like the starting article of computational social science, it was basically like the entirety of social and human footprint digitally, with the entirety of platforms and the entirety of the methods in order to provide new insight. This I would say is like, I mean, Ollie is very modest, of course. He says this is not like technically advanced, but I mean, this was I mean, in terms of like thinking about a very big topic, which is like you're mentioning war crimes, you're mentioning like internationally sanctioned activity, which is very difficult to detect, and using actual open access sources with I wouldn't say minimal. It's I think like like quite an intermediate level of technical know-how, but nothing secret, nothing that requires a lot of payment, and you're able to answer that question just being like technically innovative. So I would say like this is I think a computational social science. I mean, I don't know if you call if you would call it that way, but this is like a computational social science project of, I would say, one of the highest levels of sophistication, maybe not like lines of codes, but in terms of the way it approaches a very huge and unanswered question, and basically how it answers that question in the kind of simplicity and in the kind of scalability that it does. I would say it's like one of the frontiers of the discipline as it is in 2023. So I really think this is an extraordinary project, again, like not in the complication of the codes, but in terms of how it thinks about a complex issue and how like nicely it answers that question. I think this was really, really brilliant. Please join me in congratulating Ollie, thank you so much. Probably we all are going to ask you a ton of email questions in the coming days. So thank you so much for joining us. And let me know when you're in Istanbul so we can just catch up, okay?
Fantastic. Well, thanks for having me. It's been a pleasure.
Of course. Thank you. Bye-bye.